Welcome to our fourth class, which is going to be about classification. As usual, we will be starting with the summary of the last week. It was a crowded week last week. We had a lot of content. You should definitely check the previous lecture, listen it from YouTube, and you should check the content of the previous class. I strongly suggest you go through our examples, the hands-on examples, and then you should try to do the homework. That's pretty important. Okay, so outline of this week. We will be starting with the summary of the last week. Then we will start with a new topic called Logistic Regression. That's one type of classification, as we will be seeing. And then we will be working on MNIST database, which is a pretty famous database for artificial intelligence studies. And then we will be working on performance evaluation, as we did last week. The things we used last week concerning the performance evaluation, they were mostly for regression problems, for linear regression, polynomial regression. This week we will be working on classification problem. So the performance evaluation, especially the precision recall, will be pretty specific to this week. Okay, now let's start with the brief summary of last week. As I said, it was a crowded, very busy week last week. We saw RANZEC, and then we have seen it can handle noise data in a very good way. And it's not just for fitting a line, but we could fit a circle or whatever mathematical model we can imagine with RANZEC. Then we worked on performance metrics for model evaluation, such as residual analysis, mean square error, and R2 square calculation. Then we worked on multiple regression. And then we worked on something called regularized regression. Then we worked on polynomial regression. Then we saw something called bias variance trade-off. Okay, coming back to RANZEC, which was random sample consensus, we saw that linear regression doesn't really work, or the least square solution doesn't work very well with noisy data. And we talk about noisy data. You see, these things are noise, okay, and this could be a pretty much nice line, but these things are noise. So if you want to fit a line by using least square solution, that's not possible. Therefore, we need to find another way. So what we worked on is RANZEC. So the idea behind RANZEC was pretty simple. We randomly select minimal subset of points that we could use for our hypothesis. In this case, since we would like to fit a line, the hypothesis requires 2 points, right? So we randomly select 2 points, as in this case, and then we create our hypothesis. Our hypothesis is this line, right? And then we create a boundary, such as this boundary, and we find the distance between all the points on our line, and we select the points that falls within our error boundary. Remember, this was our error boundary. These are the lines, these are the points that fall inside our error boundary, and we calculate the number of points that fall inside our error boundary, and we repeat this. We select again randomly 2 points, and then we repeat this process until we find a meaningful line that covers most of our lines. Okay, by just using the power of randomization, we created a model that can cover most of the points by fitting a line, even though our dataset is pretty noisy. So that was basically what we saw concerning RANZEC. Then we saw 3 methods for model evaluation. And then we said, in order to create a meaningful model, we don't use the whole dataset. Remember that. We split this into 2, the train set and the test set. And we have 3 methods. The first method is somehow a visual method. We call it residual analysis. In residual analysis, what we actually do is we find the difference between our prediction and the actual data, and we check these residuals whether it's quite similar for the test set and the train set. That was the first check, remember. We check whether the shape of the residuals, the blue dots and the orange dots, are similar. The second check was whether the data is distributed randomly along zero, along this line, right? So the data, for example, in this case is pretty much distributed randomly, which means the residuals are not too big. When we observe the residuals for training and test data, their shape is quite similar. So that was what we did for residual analysis. So the mean square error is pretty simple. We find basically the difference between our observation and prediction. So that's the measurement, that's the prediction, remember, for the measurement or the prediction. We find the difference between these two. We take the square because we don't want a negative value to cancel each other. And then we take the sum of that value. That's the mean square error. That's something we use quite a lot. And then we saw another method called the coefficient of determination, or R2 method. That's basically measuring the residuals as well. And if it is close to 1, then our model is good. If it is close to 0, then our model is bad. And as a rule of thumb, if R square is around 0.5, then there's something fishy going on with our model. So that was about the performance evaluation from the previous week. And then we saw something called multiple regression. You don't need to remember all the mathematical details, but we used our overdetermined solution, the pseudo-inverse formula for the multiple regression. And the problem we were trying to solve is if we have more than one independent variable. Remember our second week when we were dealing with linear regression, we had only one independent variable, that was x, right? And we had measurements on y. And our linear regression was trying to fit a line, for example, to our x and y values. If we have more than one x, x1, x2, xn, then that problem is multiple regression. The mathematics is quite similar, but the biggest difference is if we have more than one independent variable, we're supposed to use multiple regression. And then we saw something called regularized method for regression. That was actually another alternative for Ranzek. If we have noisy data, then using a strict method like least square was not a good thing. So we were basically introducing a penalty term. And we saw three methods: ridge regression, lasso, and elastic net. And this was a combination of the first two. This was an L2 norm, this was an L1 norm method. Then we saw something called polynomial regression. As we see in this figure, our data may not be a simple line. And it usually isn't. It's usually a more complex distribution, and we usually need a more complex mathematical model. So a polynomial is definitely a more complex mathematical model than a line. And polynomial regression is trying to fit a polynomial, a degree 2 to degree 3 polynomial, for example, to the data set you provide. So that was the polynomial regression. Again, we were using the pseudo-inverse formula for derivation of the polynomial regression. And then we saw something called variance-bias trade-off. We saw two concepts. We saw something called underfitting, as in this case, and we saw something called overfitting, as in this case. And in the underfitting scenario, we have these dots, okay, and the orange curve is the perfect model. And in the underfitting scenario, we have a very simple model that doesn't really model our data set in a good way. Okay, that's too simple to model our data. And in the perfect scenario, our model is pretty close to the perfect model. And in the overfitting scenario, as in this case, the blue very complex polynomial, it's a degree 15 polynomial, our model is passing through exactly almost all the points on the dataset, right? So that's a very complex model, but it's not fitting the perfect model in a good way. For example, you just select a point here, right? And the value we would expect is something here. We selected something here. When we look at our distribution, that's something supposed to be here. But with our perfect fit overfit model, the value we would find is somewhere here, right? So that's not a good prediction. And we said our model should be simple enough to model the data, but it shouldn't be too simple, as in this case. If it is too simple, then it doesn't model our data in a good way. But if it's too complex, then it overfits to our data sets and it cannot generalize. So that was the variance bias trade-off. Okay, that's basically the quiz tree from last week. RANSAC stands for random sample consensus. Which of the following can be used for performance evaluation? We saw that all of them could be used for performance evaluation. The third question was from the previous week. Which commands we use to read the CSV files with pandas? That's read CSV. Multiple regression makes use of more than one independent variable. That's true because that's basically what it's used for. Which of the following is a regularized regression method? All of them are regularized regression methods. In the sixth question, we revisited the equation of a line. That should be pretty simple. Polynomial regression is still type of a linear regression. Some of you couldn't answer this correctly. That's true. Linear regression can handle noise data very well. No, that's why we have RANSAC or regularized method. As bias increases, algorithm may miss relevant relationship between features and the target outputs. Which command we use to calculate coefficient of determination? That's R2 square. That was something we saw from our hands-on training from the last week. Okay, so now let's start the content of this week. We will be starting with logistic regression, and then we will be seeing examples from MNIST database. So what is logistic regression? Before that, let's try to find out what actually classification is. Classification is the division of things into groups by type. As in this example, we have cats and dogs. On the left side, on the right side, we have classification methods. As you see, logistic regression is one of them. Support vector machines, a technology that we will be seeing next week. Decision trees, nearest neighborhood, these are all classifiers. So the classification is basically the division of things into groups by type. And in this problem, we would like to divide our cluster of cats and dogs into cats and dogs. So assume that this robot, this guy, this little guy here, is taking sample from this cluster and classifying it as a cat or a dog. So as you see, it's trying to put all the dogs on the left side and all the cats on the right side. As all the algorithms or all the statistical tools can do, our robots can also make mistakes. So this is definitely a cat, for example, but our robots classified this guy as a dog. So this is a cat, but it is wrongly classified as a dog. And the same is here. This guy and this guy are definitely not cats, but our robot or classifier classified these dogs as cats. Okay, so remember, the definition of classification is the division of things into groups by type. Our classifier can use different technologies such as logistic regression, support vector machines, decision trees, and k-nearest neighborhood. And our classifier, in this case our robot, classification robot, or the classifier, can make mistakes. And we will see the definition of these mistakes, and we will see how we can evaluate the performance of our classifier by using these mistakes. So what is logistic regression? Logistic regression is a binary classifier. So it decides whether an observation is from class 0 or class 1. A binary classification, as the name suggests, can group our types into two. That's either class 0 or class 1. So more complicated classifiers such as support vector machines, even some types of logistic regression can classify in our clusters. So this is the cluster, our clusters into more than two classes. But as the sake of simplicity, and in order to understand the mathematics behind logistic regression, we will be using the logistic regression as a binary classifier for this lecture. But just remember, in Sklearn, you will be able to use logistic regression as a classifier, not just as a binary classifier. So what is logistic regression? As we said, it's a binary classifier. It decides whether an observation is from class 0 or from class 1. And it is based on a very famous function called sigmoid function. So this sigmoid function is very popular, especially in deep learning. Therefore, I would just like to show you how we can derive the sigmoid function. So that's basically 1 over 1 plus e to the power minus x. Okay, so that's a very basic Python code here. We create 10,000 samples between minus 6 and 6, as you see in this plot. And then that's our sigmoid function. Okay, 1 over 1 plus e to the power minus x. And so this is how the sigmoid function looks. Basically, at 0 it's 0.5, then it goes to 1 on the right side, on the left side it goes to 0. So this is the function we will be using a lot for today's lecture. That's basically called the sigmoid function. Okay, so let's try to understand the intuition behind logistic regression. Assume we have measurements, weight measurements for mouses, and we want to know whether a mouse is obese or not. Sorry for the typo, that's supposed to be a mouse, that's not a cat. So we have measurements, weight measurements on the x-axis. On the y-axis, in linear regression, we have a continuous scale, right? In classification, we don't have a continuous scale, we just have these classes, discrete classes. So it's not continuous, but it's discrete. So either the mouse is not obese or obese, right? Depending of its weight. So instead of fitting a line to the data, logistic regression fits an S-shaped logistic function. As we saw, that's called the sigmoid function. So by just fitting this sigmoid function to our data, we create our mathematical model. We will see how we can create that S-shaped mathematical model, but assume that we have a magical way right now that we could be able to find this curve. Okay, so this is our mathematical model, and these are all probabilities. Here the probability is 1. For example, here the probability is 0. And the curve goes from 0 to 1, as we see in the figure. So if we weight a very heavy mouse, as in this case, we can definitely classify it as obese, because the probability of being obese is 1, and the probability of being not obese is 0, because it falls here, right? But if we measure a weight over here, okay, then there is 50% chance that this mouse is obese and 50% chance that this mouse is not obese. And if you weight something here, there is only a small probability that a light mouse such as this one is obese, but there is still some probability. If the measurement was close to this point, then it was definitely not obese mouse, but here there is still a small probability that the mouse is obese. So I hope you understand the logic actually behind logistic regression. So we said we use the sigmoid function, 1 over 1 plus e to the minus x. That's the sigmoid function. So for n independent variables, the probability of being class 0 is calculated with the following formula. The formula looks a little bit complicated, but don't worry, that's a pretty simple formula. You will not be implementing the formula as it is, but we will be using again scikit-learn. But just to understand how we can basically use the mathematics behind logistic regression, try to follow this. So that's the formula where bi is called the coefficient, and our aim is to predict those coefficients, right? And for n independent variables, we have n plus 1 coefficients. Why? Because as you see in the formula, that's b0 plus b1 times x1, bn times xn. Right? We have n independent variables. These x's are our independent variables. We have n of them. And we have another coefficient, this b0 here. Therefore, if we have an independent variable, as in this case, we need to find n plus 1 coefficients. Okay. So we said the probability of being class 0 is calculated with the following formula. The thing is, we have quite a few coefficients if we have n independent variables, so that's very difficult to solve mathematically or algebraically. So we use something called stochastic gradient descent. You should remember this term. We will not be using stochastic gradient descent for logistic regression quite a lot, but you will be seeing this term when we start dealing with deep learning, so you should understand what the stochastic gradient descent means. So gradient descent, not the stochastic gradient descent, is the process of minimizing a function by following the gradients of the cost function. I hope you remember the term gradient from our second lecture. So the intuition is, imagine we put an agent into this multi-dimensional plane. In this case, that's a three-dimensional plane, and that's basically our cost function. Okay, and remember from our second and third week classes, our aim is to minimize this cost function somehow. And stochastic gradient descent or gradient descent is a method, a technology that we can use to minimize this function. So the cost function hills are the maximum points, and these valleys are the minimum points. Okay, and our aim is to find these very deep points with gradient descent. So how does it work? Imagine we put an agent into this multi-dimensional plane, and the starting position is given randomly. So the guy could start here, 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 somewhere. So in this example, one of the agents started from here, for example, and the other agent started from here. We need more than one agent because we will be seeing something called local minima. While we are minimizing a function such as this one, we would like to find the global minima. And the difference between local minima and the global minima is, let's say your agent is walking in this direction, and somewhere here it found something minimum, and then it started raising. But we know that the deepest point of this hilly shade, this structure is somewhere here, right? So the point here is called local minima. The deepest point of the cost function is called the global minima. So our aim is to find the global minima. Okay, we put an agent, or we put more than one agents, the agent can only see one thing, and that's the rate of change of cost given a unit change in the coefficient. So that's basically the gradient. And there is another term called learning rate. Learning rate is another term that we will be using a lot, especially with deep learning. But most of learning algorithms, this learning rate concept refers to how large a step the agent takes when traveling. Okay, so we have gradients, we have learning rate. Given many repeated steps, the agent will slowly descend, that's why it's called gradient descent, to the lowest points in the mountainous region. So let's repeat. We put an agent here. The agent can only move in the direction of gradient. So it can only go downhill. That means moving in the direction of gradient means the agent can move only downhill. Okay? And the learning rate refers how large a step the agent can take in one step. So this distance between 2 points, that's the learning rate. Okay, this direction that the agent is going downwards, down the hill, that's gradient descent. So what was our aim? We were trying to find the lowest point, and we started with more than one agent because we could miss actually the deepest point, or we could find a point something like this. For example, we put an agent here, it started descending in this direction, it descended here, 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 and this is a minima, right? There's no going down from here. Most probably you should just go up from this point. So this is a local minima. In order to avoid local minimas, we need to use more than one agent, and we assume, as in the case of RANZEC, one of our random agents can actually find the global minima. Okay, so how does this logistic regression stuff work? Actually, that's a pretty simple algorithm. We will be seeing some Python code about how does it work, and then we will be seeing how we can implement this with scikit-learn. So each time we are given a training instance, we calculate a prediction using the current values of the coefficients. Remember, we would like to find B0 from Bn. Okay, we would like to find these guys. We make an initial prediction for all these B's, and then we calculate a prediction using the current values of the coefficients, and then we calculate a new coefficient value based on the error in the prediction. So let's try to make an example. We have these guys, two independent variables, which means we need to find three coefficients, right? We have two independent variables, x1 and x2. In each row, you find the value of x1 and x2, as well as the class that these guys belongs to. So for example, in the first row, we have these values for our independent variables, and its class is 0. And we have these guys, and their class is 1. Okay, so let's try to find out our coefficients. As I said, we have two independent variables. Therefore, we need to find basically three coefficients, B0, B1, and B2. So we need to find an initial value for our coefficients. Assume we just take 0, for example, as B0, B1, and B2. The first training instance is this one, right? So we make a prediction with our formula, this formula. This pretty complex looking but very easy formula. So we put all the numbers here. B0 is 0, B1 is 0. Basically all of the terms are 0. That's basically 1 over 2, that's 0.5. Okay, So what's the second step? We calculate new coefficient values based on the error in the prediction. So we will be using this formula. Remember, we had something called the learning rate. That was basically how long or how distant our agent could go in one step. Okay. So the new prediction for B values is B old plus learning rate times the error in this form. Okay. So we put all the numbers into the formula in order to calculate the new B0. So it's basically the initial B0, which was 0 in this case. We took learning rate as 0.3. There is no rule of thumb for learning rates. But I can just say, if your learning rate is too small, then your function learns pretty slowly. That's not a good thing. If your learning rate is too high, you can basically miss the minimum of the cost function. That's not a good thing as well. So you need to try some values for the learning rate, and you should decide which one is good for you, for your problem. Okay, but the learning rate is pretty important. You may miss the minimum of the cost function if you use a very high learning rate. So basically, by using this formula, so y is 0. Remember, from the first row it's 0. Our prediction is 0.5 times our prediction, which was 0.5, times 1 minus our prediction times x. Okay, so that's basically we take 1 for the B0 coefficient because we have no x here, right? This is basically B0 times 1, B1 times x1, that goes on like this. So that's why we have a 1 here. Okay, so x is 1 for our B0. For B1, so B old is B1, that's learning rate times the old value of the measurement here, that's 0, 0 minus our prediction, times our prediction, times 1 over our prediction, times x value, which is 2.78 in this case. So that's a very basic, very simple formula, right? And we do this a lot of times for our dataset, and each iteration that passes through the whole dataset is called an epoch. Please remember this term as well. That's an important term. And at the end of each epoch, we can calculate the error values for the model. And once we are satisfied with our accuracy, that means our learning is complete. Okay, let's now go through our hands-on training for logistic regression. So this is basically what I have shown you in the slides. We are importing our libraries as usual, and this is basically our sigmoid function. You can just give it a try. You can increase and decrease the number of samples here. You can modify these guys, and you can see the shape will always be an S shape for the sigmoid function. So how we can make a prediction with our coefficients? Assume we are given 2 coefficients. So we would like to find out this formula. We have one independent variable in our case. So this is a very simple data set. We have one independent variable and 2 classes, 0 and 1. And we would like to fit a logistic function to this data set. We will first find out how we can use the coefficients. That's basically using the formula 1 over 1 plus e to the power the beta 0 minus beta I xi. So that's basically just using the given coefficients. So these coefficients are given, we didn't calculate these guys, and we just find out the probabilities by using our famous formula, the logistic regression formula. So okay, let's try to see what happens. So for the first guy, our probability is 0.2, right? So that's smaller than 0.5. That means that's highly likely that it's from class 0. So we put a threshold. These are our prediction probabilities. We will be using a threshold. For example, we use 0.5 in this case because we use the function round. Round uses 0.5. If something is bigger than 0.5, then it is 1. If something is smaller than 0.5, then it is 0. So our prediction is class 0. And the actual value is class 0. No problem here, right? In this case, again, our prediction is from class 0 and the actual value is from class 0. That goes like this. So 2, 3, 4, 5. The first 5 samples are supposed to be from class 0. As you see, the first 1, 2, 3, 4, 5 samples are from class 0. But this is pretty fishy. This is 0.4955. It was slightly higher. If it was slightly higher, then it was going to be from class 1. Right now it's from class 0. And it is basically from class 0, actually. But if this prediction probability was slightly higher than 0.5, that was going to be misclassified as from class 1. So that's basically how we would use if we have our coefficients. But of course, the main idea behind logistic regression or stochastic gradient descent is not using the coefficients if they are given, but we would like to predict these coefficients. So that's basically finding our coefficients of the mathematical model. So let's see how we can find basically these coefficients in this example. So I have provided some functions that we will be using for that purpose. So we will be dealing with 2 examples. One is kind of a smaller example that we will be using, and the other one is a more complicated, complex example, and we will be using PyCharm in order to debug that. And you will be seeing how we can use PyCharm for our studies with this example. So as usual, we imported math in order to import exponential because we are trying to find this term. So that's basically how we make our prediction with our coefficients. That's what we did in the previous example, right? Given our coefficients and given our independent variables, that's how we make a prediction that returns a floating point. So what we have seen with the stochastic gradient descent, that was an iterative algorithm, right? Therefore, it was using a learning rate, it was using number of epochs, and it was using a training set. And in order to initialize our coefficients, we assigned 0. Remember from our slides, we assigned 0 for all the coefficients, and we iteratively try to solve the problem. Remember, the number of epochs is each iteration we pass through all the data in our data sets. So we calculate the summation of the error for each epoch and for every row in our training set. So this is going to be our training set. That's a pretty simple training set. We have basically 2 classes 0 and 1. We have a couple of rows. For each row, we make a prediction. Remember, y hat is our prediction. Okay? And then we calculate the error between the actual class and the predicted class. So this is not an integer. This is basically a floating point, and the error is therefore a floating point. and then we basically calculate the square of the error so that we are not affected with plus and minus sign from this operation. Okay, and this is basically the formula we use to update our coefficients. So the initial coefficient was updated with x is equal to 1, and the rest of the coefficients, independent variables, will be updated within a for loop. So these three lines are basically updating our coefficients. Okay, so shift enter. So this is our data set. We have a couple of rows here. We have the class as the last column. We have two independent variables for this example. We have learning rate as 0.3. We have 100 epochs. Okay, and now we would like to find out the coefficients. So let's, you see, we have always the same learning rate. That's what we provided to the function. In epoch 0, you see we have sort of a high error, and with each epoch, as you can observe, the error is decreasing, but the rate of decrease is not that high. You see, at some point, number of epochs was 100, which seems to be quite big for this data set. I mean, 10 epochs could be fine, or I don't know, maybe just, for example, 25 epochs would be sufficient for this example. And at the end, with 100 epochs, we calculated three coefficients. We calculated three coefficients, remember, because we had two independent variables. This is B0, B1, and B2. And if we want to make a prediction with our predict function, which we used in our stochastic gradient descent function as well, so we have predict. Now we have the fully predicted coefficients. We can make prediction on our data set for example, that's 0.05, which means this is supposed to be from class 0. Let's see whether that's correct. Dataset 4. Let's see, that's 0, 1, 2, 3, 4. That's from class 0. So we made a correct prediction. See, that's class 0. And what we predict is 0.05. This is smaller than 0.5. That means that's from class 0. Now let's make a prediction for dataset 6. That's very likely that it's from class 1. So if we count, that's 0, 1, 2, 3, 4, 5, 6. That's from class 1, you see. Which means actually we made a good work with predicting our coefficients. Now we have our coefficients, which we calculated with stochastic gradient descent. And we can basically make use of these coefficients in order to make predictions with other independent variables for this data set. Okay, so that was a rather simple example for logistic regression. Now we will be using a data set called PIMA-Indian diabetes data set, which I provided you yesterday. The data set is in your data folder, and I provided you all these Jupyter notebooks as well. So this is slightly a more complex example. That's again doing the same thing. We are reading our CSV file. We don't have the column names in our CSV file, so we are assigning our column names. Now I'd like you to see something. So we have 1, 2, 3, 4, 5, 6, 7, 8 independent variables, right? We are supposed to then find 9 coefficients. But the problem here is we have something called NTP. You can basically find the definition. That means, for example, number of times pregnant. That's a data set for predicting whether a patient is diabetes or not. We have age here, we have other stuff here. But the thing is, they are all from different spaces. So this is a pretty big number, right? Than this one, for example. So age is quite big from this guy. If I use these numbers as they are, then it is quite likely that these big numbers will dominate my predictions because they're high. But high doesn't mean they're important, they're just high. So I need a process called normalization. Okay, so I need to normalize all my columns with respect to, for example, the highest number in my column. Okay, once I normalized my data, I can do my predictions with this normalized data. So I provided you two functions that can normalize a given data frame. So what this is basically doing is that's taking a column here that's using a pre-processing normalization method from Sklearn. What it is doing is basically getting the maximum in this column and then dividing every number into the maximum. Okay, that's what it's doing. This is one way of doing that. This is another way of doing that. This is Sklearn doing it. And this is still Sklearn doing it with just one command. Okay, they're both equally doing the same stuff. So let's see what happens when we normalize our data. I just created a deep copy of my data frame. So that's basically my initial data frame, right? This is what I have when I normalize my data. In my normalized data, I basically printed the maximum of each column. For example, the maximum of the first column is 17, as you see. If I divide 6 into 17, 6 is this guy, the first number in the first column, I get this. So let me see what happens to my data frame. You see, this was the initial data frame with age being 50, 31, stuff like this. But now I have numbers between 0 and 1. So this is called normalization. And if we don't normalize our data, especially in logistic regression, the big numbers may dominate our predictions, which we don't want. We want all independent variables have the same contribution, unless otherwise stated. Okay. And let's see whether the second method I provided you is doing the same. You see, it's exactly the same. It's basically the same normalized data. Okay, so now we have a little bit more complex example. I would like to use another method to show you how we can deal with this kind of data. In Anaconda Navigator, you see we have quite a lot of tools. There is one tool I would like to share with you, that's PyCharm. So that's basically an integrated development environment. We have two types of PyCharm. That's one for community, as this one, and there is one professional that's usually used for commercial purposes. For education and other stuff, you can use the community edition basically. And the good thing about PyCharm is you can debug your code. Okay, these are basically our functions. You can go through that yourself. You should basically do that. These are normalization functions I provided you. These are the imported libraries. So we have a concept called cross-validation split. We are taking our data sets and we are splitting our data into n folds. We will see in the next lecture what I mean actually with the folds. And then we have an accuracy metric that basically calculates how much my prediction is correct. What's the percentage of my correct predictions. So that's the main function we will be using. And these are basically the predict stochastic gradient descent. These are functions for logistic regression, and this is basically the logistic regression. Okay, so in order to debug, you will see what I mean with debugging. I just initiate my environment, and by simply pressing F8, I can execute these lines. Okay, this is debugging, and you know what is good with debugging, you will see basically. For example, you can see the content of this data frame in a couple of ways. You can use your mouse in order to gather insights about the content of your data frame, or you can basically right click and then say evaluate expression, then you can see the content of your variable, for example. So this way it's easier to understand the content of the code. So we basically normalize our data frame. Okay, so learning rates we know, number of epochs we know. There is something called number of faults. So we will be splitting our data into faults so that we don't use the whole data for training. So for example, we will be splitting our data into 5, and we will train in each epoch, we will train our data set 5 times. So that's why we have unfolds. And we have our data sets. Now by using F7, we will go inside our algorithm. Okay, so the first thing we do is we find the faults. Let's use F7 in order to go inside this method. So what this is basically doing is we have the whole data set. Okay, now let's evaluate what's inside our whole data set. That's basically a list, and that's something like 750 lines of data. We have 8 columns of independent variables, and in the last column of each row you see the class. So we have 9 columns for each row. So we will be splitting our data into 5. That's basically how we do it. We create an empty list and then we copy our data sets. Now we find the size, fault size is how many rows each fault will contain. So remember how many faults we have? We have 5 faults. And let's find out what is basically the number of rows in our data. We have 768 rows of data, which means in each fault we will have 153 rows. Okay, so for every fault we will be basically creating our new list. So if you press F9, you can skip this for loop. That's a pretty long for loop. You can basically skip into this. So let's find out what this is actually. So we had 5 as the number of faults, right? Now we have 5 lists, and in each list, as you see, we have 152 rows, right? And we will be using these rows in order to calculate our coefficients. So here we calculated our faults. Now we will be creating some score list. As I said, for each fault we will be doing the training. Okay. So but this line is just taking all the rows in the faults and then removing the current fault from the training set. So we need a training set and a test set. Remember from our previous studies, we need a training set and a test set. And for the training set, now let's look at what we have inside the training set. We have basically 4 lists. We had 5 folds. We will use one of the folds for testing. We will use rest of the 4 for training. So right now we have, as you see, 4 lists. And with this command, we combine all the rows inside the training set. Now we have all the rows in one list. Okay, and we have our test set. Here we arrange our test set. Not gonna go into the detail. And this is the important part. We provided logistic regression as the algorithm. So let's press F7. So basically, this is the function we went through in the previous example. That's the stochastic gradient descent. We have our training set. We have our learning rate as 0.1, and we have 100 epoch. Let's go inside that. So that's basically calculating the coefficients. It's initializing our coefficients. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 coefficients. Remember, we had 8 independent variables. We have 9 coefficients that we need to calculate, and this is the initialization. We initialized all the coefficients with 0, and then for each epoch we are supposed to have 100 epoch for each fold. We will be calculating our coefficients, and then we will be returning that coefficients. So that's a pretty long operation basically. So for the first fold we calculated our coefficients, and then we will do the same thing for the other folds. So that's basically how we use PyCharm for our studies. That's one thing. That's a more comprehensive and complete example about stochastic gradient descent, logistic regression, how we can use more than one independent variables in logistic regression, and how we can use the term called folds. So we split our training data into folds, smaller groups, and we use the smaller groups for training. So that was basically it for the first lecture. So in the previous lecture, we had seen what logistic regression is. We saw how we can implement it in Python. And we saw 2 examples, one with Jupyter Notebook, one with PyCharm. Now we can actually basically use just scikit-learn in order to make coefficient estimation as well. And this is a preferable method. You will see why. As we discussed, we can use stochastic gradient descent in order to make predictions on the parameters. But this is not just one way of doing that. We can use other optimization methods, and scikit-learn is basically providing you quite a lot of functions for making the predictions. So let's spend some time how we can use scikit-learn. That's basically a linear model. Again, logistic regression. Now we are providing our data set. That's basically a couple of rows. We have one independent variable, x1, and we have our class as 0 and 1. So that's basically our data set. Now we are converting our data set into x and y, so that we can provide it to scikit-learn. So x is basically our first column, and y is basically our second column. So the way we create our model with logistic regression in scikit-learn is quite similar to the way we create our other models, like such as linear regression or polynomial regression. We just provide the name of our model, and we provide the coefficients for the model. I provided you the link for scikit-learn. You can basically check what all these parameters mean, basically. But there are couple of important parameters that you are supposed to remember. We have penalty, we have solver. That's the most important parameter. We can use quite a few solvers, as you see from the documentation. Please go through the documentation and try to see what we can do with all these parameters. So basically we are using this guy as the solver. We could use stochastic gradient descent. We have other methods as well for logistic regression. So we basically create our model as we did before. We create our model and we fit our model, right? Here we fit our model, then we make a prediction, for example. So that's basically 1, 2, 3, 4, 5 zeros, 5 ones. That was basically our data set. That's 5 rows of class 0, 5 rows of class 1. We made the perfect prediction. And there is another command here, predict probability. That's basically providing you, so this guy is providing you the classes, right? So that's providing you whether your prediction for the zeroth element is from class 0 or from class 1. So that's the concrete prediction. But if you are interested in the prediction probabilities, this predict proba is basically giving you the probability of being from class 0. So for the first row, which is predicted as 0, the probability of being from class 0 is 0.99, which means that's basically from class 0, and the probability of being from class 1 is very low for the first row. So you can basically see for each potential classes, since we are dealing with binary classification, we have 2 classes. For each classes, you can see with predict proba the prediction probabilities. That's an important phenomenon because you would like to use another threshold from 0.5 basically. You could, for example, use 0.8 as a threshold, and this guy then would be classified as from class 1, right? But since we are using 0.5 as our threshold, this guy is classified as from class 0. Okay. So for logistic regression, in order to wrap up the stuff, that's providing you a binary output. That's for binary classification. It doesn't work well with noise. So please try to remove noise before you use logistic regression or use a more complex mathematical model. And it doesn't work well with correlated inputs. You are supposed to remove multiple highly correlated inputs if you are planning to use logistic regression. Okay, so that was basically it for logistic regression. Now we will be dealing with a more fun stuff, that's MNIST database. So what is MNIST database? That's basically a database of handwritten digits. As you see, these guys are 0, that's 1, 2, 3, 4, 5. That's handwritten digits. And that contains 60,000 training images and 10,000 test images with their corresponding labels. Yesterday I provided you the dataset as tar files. Please check that files. Please try to use that files. MNIST database is an important database for artificial intelligence and machine learning. We will be using this database for deep learning as well. And you most probably will see this database quite a lot. So try to understand what it is. So basically, as I said, that contains 60,000 training images and 10,000 test images. And the files I provided you are basically 4 files. These are basically train images, train labels, test images, and test labels, each containing for training 60,000 labels and images, and for testing 10,000 training images and training labels. So what does actually this data contain? That's basically a 28 by 28 matrix. That's an image actually. That's an image of 7, right? And the way we store images are two-dimensional matrices. And this is the starting point of the matrix. So we have 28 columns and 28 rows for this small image. This is a very small image. Usually what you take with your cell phone, that's like 1000 times 1000 pixels. This is like 28 pixels by 28 pixels. And each pixel has a value of an integer that ranges from 0 to 255. And 0 means a black pixel, and 255 means a pure white pixel. So if you see a higher number here, that means it's a lighter area. And if you see a smaller number as the pixel, that means that's actually a darker area inside your pixel, inside your image. So this is basically how an image is stored. These are the pixels. Okay, so this is a completely black pixel. Each of these blocks, the square blocks, they are called pixels. Okay, this is a Snoopy image, for example, and this was an image from our database, MNIST database. This is an image of a 7, and we will see how we can read this data, how we can display this data. I provided you all the functions to deal with this data, and then we will see how we can classify this data basically. So this is a sample image from our training dataset. That's the 10,000th image from our X train. That's basically a 0. And this is basically the label of it. So this is the image of our data. X train is containing the image. That's a 28 by 28 matrix. And Y train is containing the label of that image, which basically is a 0 in our case. Okay, so let's go back to our Jupyter notebook. So that's basically this one. Our errors and stuff. The thing is, this is a function I provided you for reading the data set I provided yesterday. So this is training images, train labels, test images, and test labels. Once you call this function, that's gonna return you the X train, Y train, X test, and Y set. Okay, so if you cannot execute this, that means you are missing gzip. So please try to install this inside your Anaconda navigator. Okay, so let's try to load our MNIST data. So that was it. We basically loaded our test set and train set, and that's basically giving us the shape of our training set. That's 60,000 images of 28 by 28 pixels. Remember from the course slides, we have 60,000 training images, and each image is 28 by 28. And this is another function I provided for visualization. You can just call this function with any data and index. So what you provide is basically the index of what you would like to display, and basically the training or test data. So let's see what we have as the 600. So that's basically a 9. Let's see what we have, for example, 7,000. That's basically an 8. Okay. And in order to see the correct label, for example, for 7000, we just check the content of white train. So that's basically an 8. You see, these are the things we will be using for classification. Okay, before we proceed, we need to shuffle our data. Since stochastic gradient descent is an iterative method, if we just provide this data as it is, if we don't shuffle it, then it may not converge. So it's usually a good idea to make a shuffling inside your data so that you randomly select the consecutive training and test data. So that's basically what it is doing. That's creating you a shuffle list as the permutation. So number of splits is 60,000. That's the number of our training images. By doing this, we basically change the indices inside X train and Y train. We shuffle that indices. And you see the shuffling index shape is 60,000. That's because we are shuffling each and every training and X train and Y train for the training purpose. Okay, so what we are trying to do is we are trying to write a binary classifier so that it can decide whether a given digit is a 0 or not. Remember, we are dealing with logistic regression. That's a binary classifier. So we need to make a binary decision. So we cannot classify our data as 0, 1, 2, 3. We cannot classify our data with 10 classes. Right? We have 10 classes because we have 10 digits. But since we are dealing with a binary classification problem, logistic regression, we need to convert it to a basically binary classification. So the problem we are trying to solve is we are given a digit and we are trying to understand whether this digit is a 0 or not. Okay. So we need to arrange our labels first. For the training set, if the label is 0, we assign true, and if it is not, we assign a false here. And for the test, we do the same as well. So let's check the contents of the first 40 rows of our white train. So that's basically providing you false, 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 which means this is not a 0, this is not a 0, this is supposed to be a 0. Let's see whether that's correct. You see, the first one is digit 1, it's digit 6. This is 0. And as you see, that's true. So what we did is we assign true to the white train if that sample is a 0, and we assign a false if that sample is not 0. Therefore, we can use our white train for binary classification. Okay, so in order to use scikit-learn, we need to convert our 28 by 28 image into a one-dimensional vector. That's how it basically uses the data. Therefore, we need to convert our data into a row-wise matrix. It doesn't use two-dimensional matrices for prediction. So that's why it's called X train flat and Y X test flat. We converted both our training set and test set. Okay, let's see the shape. Beforehand, the shape was 60,000 28 by 28. Remember? And now it's 60,784. That's basically the multiplication of 28 by 28. So this is a flattened training set. 60,000 rows of data. Okay. Now we will be training our model basically. This time we are not gonna use logistic regression, but we will be using stochastic gradient descent classifier. They are basically the same stuff. They're not really that different. But this time we will be using stochastic gradient classifier. Random state means, if you remember from our last week's work, that means don't do stuff randomly when you're doing the stochastic gradient descent. Therefore, I can repeat exactly the same result. If we give this a random state, remember the stochastic gradient descent, we had our agent that was placed randomly. This is still placing that agent randomly, but each time we run this command, it is putting the agent into the same random place. It's not putting it any random place. It's using the same random place. So basically, the creation of the model is same as logistic regression or linear regression. We just call the name of our mathematical model, and then we use our data in order to fit. Okay. So that will take a little bit time. That's a big model to train. It's still okay. Now the training is over. Now we have our mathematical model, stochastic gradient descent classifier. Now we can make our predictions. So let's see what we have as the 35th element. So that's basically a 2. Let's see whether that's a 2. When we visualize it, that's basically a 2. Now let's make a prediction. 2 is not 0, right? So that's supposed to be a non-zero class. That's supposed to be a non-zero class. Now let's make a prediction. So it gave us a false, because basically it's not a 0, right? If it was a 0, that was going to be a true. Let's see what we have in 10. That's basically an 8. So I wonder what's gonna predict this as, because that looks like a 0 actually. That may predict this as a 0. Let's see. So it didn't actually predict this as a 0, but it predicted this as a non-zero. Let me check. So this is a 0, right? And let's visualize this. This is a 0. Now let's use our model we just created, how it's going to make a prediction. Okay, it predicts this as a 0. It's a true. Remember, that was a binary classifier. It was trying to classify the given image as a 0 or non-zero. It classified our all non-zero images as non-zero. It gave us false, and it gave us true for our image, which is a 0. Okay, so now we have our classifiers. We would like to actually measure their performance. Okay. The first measure is accuracy, and that's basically number of correctly classified samples over number of all samples. That's like the most basic definition you can have. That's pretty easy actually. And let's see it in action. We have our test set, flattened test set from MNIST database, right? We make a prediction for all elements, 10,000 elements in our test sets. Then for everything that are supposed to be 0, we will count the 0, and then we will divide this into the total number, which is 10,000. And see, our total accuracy is 0.98, which is not bad. Okay, so accuracy is one way of measuring things. And in order to make actually things a little bit more complicated, let me share you this stratified k-fold. That's something we did actually in the previous lecture. We divided our data set into folds, and the stratified k-fold is basically trying to resample your data sets in a way that it is basically more or less a subset of your original data sets with contribution with a weight from the original data set. For example, we have 3 people in our data sets as this class. We have 3 classes. We have this class, and this class. And we have 3 people in this class. We have 6 people in this class. We have 3 people in this class. So the contribution of this class is 1. The contribution of this class is 2. The contribution of this class is 1. So in order to create a subpopulation from my population, if I select one guy from this class, 2 guys, because this class is more crowded, 2 guys from this class, and 1 guy from this class, then that's called stratified k-fold resampling. If I were to choose all these 4 people from this class, that wouldn't be a good sample for this training data set, because we have 3 classes, but all subsamples came from the same class. So that would either cause an overfitting or an underfitting, or that would lead to a non-convergent training. So in order to make a good prediction, you should take care of the data, and in order to create good resampling, you should try to get sample from each class in your data set, and that's stratified k-fold basically. So how we use stratified k-fold? That's let's see a small example with stratified k-fold. So this is the classifier we used in the last example. You can just state number of splits done. That's basically splitting into 3 splits, for example. If you give shuffle as true, that's basically shuffling your data as I shown you in the MNIST case. And if you run this code, that's gonna basically create you 3 accuracy values, okay, for each prediction. And as you see, that's gonna take a little bit while. That was the first prediction for our first fault. That was the prediction for the second fault, and that's gonna be the prediction for our third fault. As you see, the prediction accuracy is quite similar, right? That means our stratified k-fold is splitting our training set in a good way, so that it's learning more or less the same model. If it was not splitting the training sets in a bad way, if it was splitting it in a bad way, for example, if it was splitting in a way that all non-zeros were in the training set and there was no 0 in the training set, then our accuracy would be pretty low, right? But stratified k-fold is taking care of that. But that's actually pointing a problem with accuracy. I mean, if you are using accuracy as your only metric, try to understand this problem. We have 10 digits in MNIST database, right? We have 0 and the other 9 digits. And our problem is to classify whether a digit is 0 or not. Let's say we have the world's silliest and most simple classifier which says everything is non-zero. That's a classifier. It can say whatever image you give, it's just basically saying it's a non-zero, non-zero, non-zero. And if you just use accuracy as your metric, your simple most stupid classifier will be 90% correct, because 90% of your data is non-zero, right? If you can just say everything is non-zero, then it's gonna be 90% correct. That actually means accuracy as it is, as a single metric, is not a good metric. You need to use something else, okay? And that basically is making use of confusion metrics. Okay, what does confusion metrics mean actually? We have our predictions and we have our actual labels, okay? And if something is actually positive, you should understand how we can read this confusion matrix. If something is actually positive and we predicted this as positive, then this is a true positive. Okay, remember our dog and cat classification? We classified a dog as a dog. Okay, that's a true positive, because it's actually a positive value and we predicted this as a positive, so it's a true positive. Remember our digit 0 or non-zero classifier? Let's say we gave a 0 and we predict this as a 0. That's a true positive. Let's say something is non-zero. Okay, that's actually a non-zero. Let's say that's a digit 1 and we predict this as a 0. That's a false positive. Let's say something is a non-zero and we predict this as a non-zero. That's a true negative. And we have another term called false negative, which means that's basically a 0, but we predicted this as a non-zero. So the confusion matrix, that's something we will be using a lot. And basically, we will see a Python example how we can create our confusion matrix. But before going into the Python code, I would like to talk about the terms precision and recall. So the precision and recall, we will be using these terms a lot. So precision measures the accuracy of positive predictions. Okay? And the basic definition of precision is true positives divided into true positives plus false positives. So this is basically the definition of precision, and this is the right side of this confusion matrix. This guy is called confusion matrix because that's basically giving you whether you confused something with something else. Okay, so that's basically called the confusion matrix. And recall actually means the ratio of positive instances that are correctly detected by the classifier. And the formula for the recall is true positives divided into true positives plus false negatives. Basically, precision means how well you can find something. I mean, you can find stuff. For example, let's say you are trying to detect airplanes on an image. Okay, let's say we have 100 airplanes, and then let's say you found just 10 airplanes on that image, but you didn't find anything else. Okay, that means your classifier is having a very high precision because it didn't find anything wrong. That's precision. If you find something wrong, your precision decreases. Okay, but we had 100 airplanes inside my image, but I just found 10 of them. That's the problem with recall. I couldn't find 90 of my airplanes, right? Then my recall is 10%, which is pretty low. So recall is how many of the items I could find. Precision basically means how accurate I could be able to find these items. The precision and recall metrics are used together. None of them are good for good as a metric if you don't use the other one. For example, you can't just use precision or you can't just use recall. You should be using both precision and recall together. So let's make a toy example and assume we have an imaginary classifier called GIMP shape classifier, and it classifies shapes as either fox or pepper. Okay, that's the problem we are trying to solve. We have an image, we have foxes and peppers inside that image. Then we would like to classify these guys. So assume blue rectangles are shapes that are classified as pepper. Okay, if you see a blue rectangle here that is classified as a pepper, that might be a pepper or that might be a fox. So this is correctly classified because this is a pepper and my classifier said this is a pepper. So no problem with that. But this is a fox, but my classifier said this is a pepper. So this is wrongly classified as a pepper. And red rectangles are shapes that are classified as fox. So this guy over here and this guy over here, they are correctly classified because they are foxes, and my toy classifier classified these guys as fox. So these are true positive. Okay, and this is a pepper, but my toy classifier predicted this as a fox. This is a wrong prediction. So we have 10 peppers and 10 foxes in my example. My classifier correctly classified 7 peppers as peppers, classified 3 peppers as fox, correctly classified 6 foxes as fox, and classified 4 foxes as pepper. So this is what happens. This is basically my confusion matrix, right? And if I put this like that, you can understand the confusion matrix in a better way. So something is actually a fox, and my predictor predicts this as a fox. And something is actually a fox, but my predictor predicts this as a pepper. This is this guy. And something is actually a pepper, but my predictor predicts this as a fox. This is a wrong classification. And something is actually a pepper, but predicted as a pepper. That's a correct classification. So let's try to put this into our formula. Let's find precision and recall for pepper classification. So for pepper classification, this is the confusion matrix. So the true negatives. Let's find the true positives first. What are the true positives? The stuff that are actually pepper and predicted as pepper. These 7 guys, they are true positives. Okay? And what are the false positives? I predict this as pepper, but they are actually foxes. These 4 guys. These are false positives. Okay? And what is important for precision recall as well, the false negative for the pepper, which means something is basically predicted as fox, but it is actually a pepper, and that's 3. Okay, and my precision is 7 over 7 plus 4, because my true positives are 7, my false positives are 4. So let me repeat. I have a classifier for pepper classification. My classifier predicted 7 of my peppers as peppers, and it predicted 4 foxes as pepper as well. Which means I have 7 true positives, I have 4 false positives, because I predict this as a pepper, but it's fox. Okay. And I have 3 peppers that I couldn't predict as pepper. I predicted as a fox or something else. So these are the false negatives. Things I couldn't find, things I found correctly, and things I found wrongly. That's an easier way to remember that phenomenon. True positives are the things that I found or I classified correctly. Okay. False negatives are the guys I couldn't classify correctly, and false positives are the guys I classified wrongly. So that way you can remember more easy actually. And you can do basically the same for the fox classification. Try to do this yourself, so you can check whether you understand the concept about the precision and recall. That's an important concept that we will be using a lot. Please try to understand the difference between precision and recall, why we should use precision and recall, why accuracy is not enough as a metric, and how we can basically use precision and recall. Please try to understand that. So let's make another example to recap. So let's say we are trying to classify dogs. Okay. If we classify a dog as a dog, that's a true positive. And if we classify a cat as a dog, that's a false positive. And if we classify a dog as a non-dog, that's a false negative. That's the guys you should remember. Okay. If I classified a dog as a dog, that's a true positive. I classified a cat as a dog, that's a false positive. I wrongly classified a dog as a cat, that's a false negative. I think that should be clear by now. So now we have another metric called F1 score. That's basically the combination of precision and recall. That's the harmonic mean of precision and recall. And the formula is pretty simple. That's 2 times precision times recall, or precision plus recall. And this way you can use precision and recall at the same time, but you still have one metric. And F1 score favors the classifier to have both precision and recall high. Why? Because if you check the formula, if your precision is high but your recall is low, then F1 score reduces. Okay. They have almost exactly the same effect, precision and recall. So it favors both high precision and high recall. If you have high precision, for example, low recall, then F1 score is low. Or vice versa. If you have high recall and low precision, then your F1 score is low as well. If you want to have high F1 score, then you are supposed to have high precision and high recall. Basically, that's a harmonic mean of precision and recall. If you want to just use one metric for your problem, you can use F1 score. But if you want to go for precision and recall, that would give you much better idea about your mathematical model for your data. So in the previous lecture, we have seen accuracy, precision, recall, and F1 score as performance evaluation metrics. Now I would like to talk about something called precision recall trade-off. So precision and recall are complementary metrics, and if you aim for high precision, then your recall may reduce, and if you aim for high recall, your precision may reduce. So you need to find a good point where you have a decent precision and decent recall. A low precision or low recall is not good by itself. So if you, for example, a very high precision but a very low recall, then your model is not doing well. That's for sure. Remember our airplane finding example? We had 100 airplanes. We could be able to find 10 airplanes. We couldn't find 90 of the airplanes, but we didn't find any wrong airplanes. Okay, the precision is perfect. The precision is 100%. But our recall is 10%, which is very bad. That means our classifier is really good if it finds something, but it's not good for finding things. That's basically the difference between precision and recall. So let's see this in an example. Remember our digit classification example. We have actual values and we have decision scores. And depending on the decision score, we will say whether the digit is correctly classified or not. And then we will find the precision and recall for all of these values. So let's say we have a decision threshold as 0. Okay. And our actual value is a 7. We have a decision score which is greater than 0. That's a 5. That means we actually classified this as a 0 with our decision, because our decision score is higher than 0, and our problem is we are trying to find whether this digit is a 0 or not. Its actual value is 7, my decision score is 5, and my decision threshold is 0. And since 5 is higher than my decision score, I classified this guy as a 0, but its actual value is 7. That's a false positive. Okay. So the digit's actual value is 1. My decision score is minus 15, which is smaller than my decision score. And I classified this as a non-zero. That's correct. That's correctly classified. But this is correctly classified as a non-zero. So my digit is 0. My decision score is quite high. That's 50. And I decided this, I predicted this as a 0, which means this is a true positive. Okay. This digit is 4. My decision score is minus 20. My decision threshold is 0. Then I decided this, I predicted this as a non-zero. That's okay. My digit is 0. My decision threshold is 0. My decision score is 15, and this is higher than 0. So this is a true positive as well. My digit is 2. My decision score is minus 10. That means I correctly classified this digit as a non-zero. This is an 8. That's a digit I could confuse with 0, right? Logically, it looks like a 0. And my decision score is 25. And my decision threshold is 0. That actually means this is a false positive. I misclassified this guy. This digit is 0. My decision score is 20. I correctly classified this. This is a true positive. This is a digit 9. My decision threshold is higher than 0. This is a false positive. So as you see, depending on my decision thresholds, I have number of true positives as 4, number of false positives as 4, number of false negatives 0. and my precision is 0.5, my recall is 1. So this was my decision threshold as 0. Let me do the same. I'm not going to go through all of the numbers, but if I use the decision threshold as 2, the false positive number of false positives reduced from 4 to 3. In the previous slide where I was using the decision threshold as 0, my false positive number was 4. Because I had this guy, I confused this with a 0. When I increase my decision threshold, since 5 is smaller than 6, I could be able to correctly classify this guy as a non-zero. So that changed my precision. My recall is still 1. So let's increase our decision threshold a little bit more. Once we increase our decision thresholds, I started to miss some zeros, right? The decision score was 18 for this guy. When I use a decision threshold as 20, I wrongly classified this, and that guy fall into the category of false negative. Again, this guy here had a decision score of 15, and this is still lower than 20, which means this fall into the category of false negative as well. Okay, so in the previous slide, my precision was 0.57, my recall was 1. Here my recall is 0.5, my precision is 0.5. You see, depending on the threshold you choose, the number of true positives, false positives, and false negatives may change, and that affects your precision as well as your recall. And once you have a decision threshold of 18, both your precision and recall basically increases. And if I choose a decision threshold as 15, then my recall is 1, my precision is 0.66. That's as good as it can get. You cannot get better than this. And if you use F1 score as your metric, you would see that that's the highest point for a F1 score. The thing is, if you plot your decision scores with respect to number of predictions, there is an overlapping region. And that means you will confuse these classes for sure. And there is no correct way, there is no way with this decision scores, you have these decision scores, there is no way you can classify these classes perfectly because there is an overlap here. So these are the zeros. So this curve goes like this. These are the non-zeros, and there is an overlap. That means your classifier, the classifier we trained in the previous lecture, there is no way it can perform perfectly. If we plot this precision and recall as curves, you can basically use these curves to select your thresholds. For example, you see here you have decent precision and decent recall. Here you have pretty decent precision, but your recall starts reducing. And if you go along this side, your precision is perfect. That's 1. That's as good as it can get. But your recall reduces to 0, which means you shall not choose a threshold for that problem we worked on. You shall not choose a threshold somewhere here because you have a very low precision. You should be choosing a value somewhere here for an ideal precision and recall value. The thing is, there is no rule of thumb for selecting your precision recall value because some tasks require very high precision. For example, if you are trying to find adult content filter for kids your precision should be very high. But some tasks require very high recall. For example, you want to find potential crime detections. Even if you have wrong detections, it's much better to be able to find the potential crimes than missing them. So depending on your problem, you may want to go for high precision, or you may want to go for high recall, but usually it's a good idea to find a decent precision and decent recall in a balanced way. And there is yet another concept curve called ROC curves. That's basically the receiver operating characteristics curve. And what it does is that's slightly different than precision recall curve. This is based on not precision recall, but it's based on true positive rates and false positive rates. And the definition of true positive rate is basically this: true positive divided into true positive plus false negative. That's basically another name for recall, true positive rate. And false positive rate is basically your false positives divided into false positive plus true negatives. In order to use ROC curves, you are supposed to have true negatives in your problem. So if you are dealing with a detection problem, it's highly likely that you will not have true negatives. So remember, if you are gonna use ROC curves, receiver operating characteristic curves, you are supposed to have true negatives. Otherwise, ROC curves doesn't mean anything. And the way we use ROC curves is we find area under the curve, and the bigger the area under this curve, the better your model is, basically. Okay, so let's go through some Python code quickly, and then we will recap the lecture. So we went through stratified k-folds. Now we will be dealing with the confusion matrix, how we can create the confusion matrix so that we can find the precision and recall. We will be using from scikit-learn model selection cross-validation predict. We will be using that command, and then we initialize random with a seed 0 for the numpy, and then we make a cross-validation prediction with our X train and Y train. Okay, and then we import the confusion matrix from scikit-learn matrix, and then we're gonna basically print the confusion matrix. The thing is, this takes a little bit time. Now it's over. We can print our confusion matrix basically. So in order to read this confusion matrix, you can use this template. That's true, negative, false, positive, false, negative, true, positive. That's basically it. That's true, negative, which means that was a classifier to decide whether a digit is a 0 or a non-zero. So these are the true negatives. These are the guys correctly classified as non-zero digit. So we have 10 digits. You know, we had 60,000 training images. Each digit has 10,000 training samples. We could be able to classify this number of training samples correctly as non-zero. Okay, these are the true negatives. And the second big number is the true positives. These are the digit zeros that we could be able to classify correctly. Okay, these are our true positives. And the rest is false positive and false negative. Basically, these guys are the false positives, which means I classified these as 0, but they're not 0. They're not digit 0. That's 8 or 9 or whatever it is. But I misclassified these guys. And these are the guys I couldn't classify as 0, but they are basically 0, digit 0. So that's my confusion matrix. And this template is how I can read this confusion matrix. Okay. Now that I have this confusion matrix, I can plot this in a fancy way. That's basically this template. Actually, you should know this template by heart. This is an important template. This is an important table. You should know this by heart. And in order to calculate the precision and recall score, we again use metrics from scikit-learn. We basically import it, and then we basically give our train labels and our predictions. Then it's calculating our precision. That's pretty high, 0.95, and we are calculating our score for recall. That's decent. That's not bad. That's not really good, but that's okay as a predictor. And these numbers may change once you're working with this Jupyter notebook, because we shuffled it randomly, we shuffled the data randomly. So when you train the model yourself, you may get different scores. So that's because the random processes that's going on in the shuffling. And if we want to calculate the F1 score, that was the formula, remember? That's basically, again, from the scikit-learn metrics, we import the F1 score, and then we just give train labels and our predictions in order to calculate the F1 score. That's decent F1 score. That's above 0.9. That means the model is doing fine. So I'm not gonna go into the details of this. That's basically the plots of this. This is the thing I showed you, decision scores versus the number of predictions. And since there is an overlap here, and these are the guys that are supposed to be classified as 0, these are the guys that are supposed to be classified as non-zero. And since there is an overlap within these two curves, that means my classifier is doing fine, but it is not perfect, and it's never gonna happen. I obtain one for precision and one for recall. That's never gonna happen. There is a confusion over here. That's basically doing that. You can just go through that, and then we can plot our precision and recall curves, something like this, so that you can decide for a threshold. For different thresholds, you can calculate the precision, both precision and recall, and then you can decide whether you want to go for a high precision, low recall, or low precision, low recall, or a balanced precision and balanced recall. That's something you should decide for yourself. And this is how we use ROC curves. Again, we import ROC curve from the scikit-learn metrics, and then we basically calculate the ROC curve with false positive rate, true positive rate. Since I didn't execute the rest of the this part of the code, I think that's giving errors just for the time problems. Not gonna execute that, but once you plot the ROC curve, you obtain something like this. Okay, and the higher area under this curve, the better it is. So ideally, you should have an ROC value of 1, which is usually not possible. But the higher values means your model is doing much better than a lower ROC curve area under the curve value. Okay, for example, in this case we have 0.9955, which is very, very high. So that concludes our theoretical and practical part of our fourth week, which was about logistic regression and binary classification.